The planet turns in silence while the night settles over continents, and a single small room rests upon a crust that never stops moving. Within that room, a resting human body lies still on a bed, unaware that the ground beneath carries every cell and every drifting thought along a path traced long before any mind learned to count its own heartbeats. Earth spins around its axis at well over 1,670 kilometers per hour, at the equator, a steady rotation that curls oceans and continents through space, like subtle brushstrokes on a dark canvas. At the same time, the entire world moves along its orbit around the Sun at nearly 108,000 kilometers per hour, following a curved track that has repeated for billions of years and yet is never quite the same twice. Above the atmosphere, the sky appears calm, the same familiar patterns of constellations and planets glimmering against the black, but underneath that apparent stillness, the whole system rushes forward through the galaxy. The Sun, with its retinue of planets, moons, asteroids, and drifting dust, orbits the center of the Milky Way at roughly 220 kilometers per second, pulled by the distant mass of a hidden central darkness. All of these motions combine into a layered journey rotation upon orbit upon galactic drift, and still no sensation of movement reaches the skin of the sleeper. The reason is simple and profound at the same time. Everything that matters to that resting body, the bed, the walls, the surrounding air, the distant mountains, shares almost exactly the same motion. The entire environment forms a single moving frame, an invisible vessel gliding through space. Within that vessel there is no rush of wind, no sense of speed, only the gentle weight of gravity pressing the body into the mattress, as if the planet were perfectly still. The oceans follow the rotation, swelling and retreating in tides shaped by the moon and the sun. The atmosphere wraps itself around the spinning sphere, carried along by friction and by gravity. Even the drifting dust within a quiet bedroom becomes part of this great rotation circling the axis of the world without the slightest awareness. For an outside observer placed impossibly far away above the plane of the solar system, Earth would appear as a tiny bright point tracing a slow ellipse around a blazing star, its axis tilted its poles, describing a subtle cone as millennia pass. That same observer, looking over even longer spans of time, would see the Sun and its planets orbiting the galactic center in a vast spiral, completing a single galactic year in hundreds of millions of terrestrial years. Yet inside the room, the only motion that registers is the small rise and fall of a chest, the slow rhythm of breathing. Time for that resting mind is measured not by orbits and rotations, but by the fading of thoughts and the gradual descent into sleep. Instruments tell a different story. Radio telescopes listen to distant quasars, extraordinarily remote and bright galaxies, using them as fixed points to measure how the rotation of Earth subtly speeds up and slows down. Laser beams bounce off reflectors left on the moon by human missions and return to detectors on Earth, revealing tiny changes in the distance as the moon slowly drifts away and the tides rob the planet of a little of its spin. Atomic clocks track the length of a day so precisely that small irregularities appear slight fluctuations caused by shifting winds, moving oceans, and the slow rebound of land once crushed by ancient ice. Agencies such as the National Aeronautics and Space Administration and the European Space Agency gather these measurements into a continuous record, a quiet logbook of planetary motion written in fractions of milliseconds and minuscule variations in angle. The picture that emerges is not of a perfectly regular spinning top, but of a living world whose rotation responds to the flow of mass on its surface and in its interior. When vast ice sheets melt and water redistributes across the oceans, the rate of spin changes by tiny amounts, like a figure skater adjusting speed by moving arms and legs. Powerful earthquakes shift rock deep beneath the crust and slightly alter the balance of the globe. None of these shifts is large enough to disturb the calm of a night of sleep, yet each one leaves a trace in the timing of the planet, a subtle signature that instruments can detect. In this way, the rotation of Earth becomes both a clock and a diary, marking the passage of days while also preserving within its small irregularities a record of changing climate, moving oceans, and tectonic restlessness. The resting body, unaware of equations or data sets, participates in all of this simply by existing on the surface. Every dream unfolds while the planet turns beneath. Every memory is stored in a brain carried around the sun. Every lifetime is a brief segment of a spiral drawn through the galaxy by the combined motions of star and planet and dark unseen structures farther out. The illusion of stillness becomes part of the story. A calm interior world rides upon a restless exterior one, and the contrast between them raises a quiet question. If the sense of being at rest can coexist with such immense movement, then the familiar experience of time may also be only a local impression shaped by motion rather than a universal flow. For now, the sleeper remains unaware, and the planet continues its silent spin, carving another thin slice of rotation into the deep history of the solar system. Far outside the quiet motions of breath and thought, another pattern unfolds, a slower and wider motion that stretches around the whole planet. Earth does not simply spin in place like a toy left on a table. It travels along an elongated path around the sun, an orbit almost but not quite circular, carved by gravity over eons. At one point in this path, the planet moves a little closer to the star-reaching perihelion, and months later it drifts a little farther away toward aphelion. The difference in distance is only a few million kilometers, a small fraction of the total span of the orbit. Yet even this gentle asymmetry changes the rhythm of motion. When Earth draws nearer to the sun, it speeds up, slightly swept along more swiftly by the deeper curve of the gravitational well. When it moves farther away, it slows, coasting through a shallower part of the same invisible valley. The result is a subtle variation in the apparent pace of the sun across the sky, a quiet mismatch between the regular beat imagined by clocks and the true behavior of the moving world. For most of history, this mismatch is noticed not with instruments, but with careful watching. Generations of observers study the length of shadows at midday, mark the earliest and latest sunsets, and trace the positions of bright stars and planets against stone and horizon. Farmers and navigators learn that the sun does not return to the highest point in the sky at exactly the same time each day. Even when the seasons seem steady, some days the star runs a little ahead of expectation, other days a little behind, painting the sky with a shifting pattern of early and late that repeats every year. In the modern age, that ancient noticing becomes measurement. Astronomers define a solar day as the interval between two successive crossings of the sun over a local meridian, the invisible line stretching from north to south across a given place on Earth. They compare this true solar time with a constructed quantity called mean solar time, which averages out the irregularities to create a convenient standard day of 24 hours. The difference between the real sun and this imagined average is given a name, the equation of time, a gentle correction that tells how far the sky's behavior has drifted from the schedule printed on a calendar. Plotted across a year, this difference rises and falls, sometimes making the true sun appear ahead, sometimes behind. When the position of the sun is recorded at the same clock time over an entire year, the points do not form a straight line, but a narrow figure 8 in the sky. This curve, the analemma, hangs above the world like a bright signature of the planet's tilted axis and imperfect orbit. Agencies such as the National Aeronautics and Space Administration extend this understanding with spacecraft that watch the sun without interruption. A satellite placed in a steady position relative to Earth records the disk of the star day after day, tracking its apparent size and location with great precision. From this data, the slight changes in Earth's distance and speed become visible, not as abstractions, but as tiny shifts in the sun's apparent path and diameter. On the ground, networks of observatories gather parallel information using carefully calibrated clocks to log the moment when the sun reaches its daily peak above each instrument. Together, these records reveal that the true solar day sometimes stretches a little longer than the average and sometimes shrinks a little shorter. The difference is small, measured in tens of seconds, but across weeks and months, it accumulates into minutes that wander ahead or behind the schedule set by human timekeeping. Mechanical clocks and later atomic ones refuse to bend with these subtle changes. They tick at their own unwavering pace, turning the drifting behavior of the sky into a quietly growing discrepancy. Noon on a clock becomes detached from the instant when the sun stands highest. In some seasons, the earliest sunset arrives before the shortest day, and the latest sunrise comes after a pattern that appears strange until the interplay between tilt orbit and speed is taken into account. For a mind lying in the dark, unaware of orbital mechanics, the passing of days feels consistent, a chain of mornings and evenings spaced evenly apart. Yet above that experience, a more intricate pattern unfolds. The planet inclines its axis, moves faster and slower along its path, and in doing so stretches and compresses the true length of a day by small but measurable amounts. The familiar 24-hour cycle becomes a careful compromise, a chosen average that covers the restless details of celestial motion with a reassuring layer of regularity. Within that compromise hides a question that sharpens as precision increases. If the day itself refuses to be perfectly constant, and if the sun cannot keep pace with the clocks built to track it, then what exactly is being counted when seconds and minutes are named? The orbit supplies one rhythm, the rotation another, and the variations caused by tilt and distance provide a third, all weaving together into a fabric of time that is at once regular and uneven. Instruments read these dissonances and correct them with tables and algorithms, but the underlying reality remains. The world does not turn and travel with the flawless beat of a metronome. Instead, it moves with a slightly shifting cadence, and modern timekeeping rides atop this living pulse like a thin shell laid over deeper tides. Beneath the small corrections that keep clocks in step with the turning of Earth, a quieter question lingers. If the planet will not rotate with perfect regularity, and the sun will not cross the sky at exactly the same time each day, what is really being counted when a second is named? For a long time, time is pictured as an invisible background that flows at the same rate everywhere, whether anything moves or not. The spin of Earth and the orbit around the sun serve as markers on that background, but the background itself is assumed to be rigid and universal. That picture begins to fail when light is examined with growing care. Experiments with moving sources and mirrors show that the speed of light in empty space is always the same, no matter how quickly the observer travels. If two distant flashes can be simultaneous for one observer and not for another, then the idea of a single shared moment for the entire universe dissolves. The special theory of relativity turns this into a clear rule. Every traveler traces a path through space and a linked path through time, and the faster the traveler moves relative to another, the more slowly all internal processes unfold when measured from that other frame. At ordinary human speeds, the difference is too small to notice, but at speeds approaching a large fraction of the speed of light, the effect becomes striking. There is no single true rate at which time flows. Each path carries its own rhythm, and comparisons between rhythms depend on relative motion. The general theory of relativity deepens this picture by tying time to gravity. Massive bodies bend the geometry of space-time around them, and in that curved geometry, the rate at which seconds pass depends on position. A clock nearer to a massive body ticks more slowly than one placed higher in the same gravitational field. On Earth, the difference between sea level and mountain summit is tiny, yet sensitive atomic clocks record it. A clock in orbit aboard a satellite feels weaker gravity and moves faster than a similar clock on the ground. Weaker gravity tends to make the orbiting clock run faster, while greater speed tends to make it run slower. When both effects are combined, the result is a small but steady offset that engineers must correct when using navigation satellites to find positions on the surface below. Without these corrections, calculated locations would drift by many kilometers over the course of a single day. Experiments continue to probe the flow of time. Atomic clocks are flown around the planet while identical devices remain at observatories. When they are brought together again, their readings disagree by the amounts predicted by relativity. Newer optical lattice clocks, which measure the oscillations of atoms held in grids of light, are so sensitive that lifting one clock by only a small height above another produces a measurable change in rate. Time itself appears to quicken or slow between floor and tabletop, valley and hill. Around dense objects such as neutron stars and black holes, the effect grows dramatic. Near the edge of a black hole where escape speed approaches the speed of light, the passage of time for a hovering observer slows almost to a standstill. From far away, events near that boundary appear to unfold as though the local clock were nearly frozen. Observations of matter spiraling into these regions show light bent, delayed, and shifted in ways that match the predictions of curved space and distorted time. All of this points toward a conclusion both simple and unsettling. What is called a second is not a universal unit fixed at the birth of the cosmos. It is a local measure set by motion and gravity, and modern timekeeping reflects this. The official second is no longer tied to the turning of Earth or the apparent motion of the sun, but to the internal rhythm of atoms, in particular the frequency of radiation associated with transitions in cesium. In controlled laboratories, ensembles of such atoms provide a reference that does not care about weather season or the slight wanderings of the planet's spin. Yet even atomic time must be connected back to the moving world on which the laboratories stand. Facilities compare their clocks, average them into a coordinated timescale, and apply small adjustments so that noon remains roughly tied to the sun and calendars remain in step with the seasons. Time becomes a compromise between the behavior of atoms and the behavior of a rotating, orbiting planet. Beneath that compromise, a deeper mystery remains. If time is always entangled with motion and with gravity, then asking whether a single true time exists apart from all change may have no clear answer. Any description of the history of the universe must choose a frame in which to count its billions of years, often one picked for convenience or symmetry. Another observer moving rapidly with respect to that frame or resting deep inside a strong gravitational field would slice the same history into different layers of before and after. The sleeper on the turning Earth follows one narrow thread through this web of possible times carried by planetary motion and gravity. Somewhere else, another traveler follows another thread, and the two threads agree on the ordering of events only when light signals are exchanged and compared. In that comparison, time reveals itself not as a substance that exists on its own, but as a relationship between sequences of change. Whether an even deeper hidden time lies beneath those relationships remains an open question hanging at the edge of understanding like a faint echo outside the reach of any clock. Far from the simple idea that noon arrives together for an entire planet, the real sun traces a more intricate pattern over Earth, and local skies follow their own subtle schedules. In earlier ages, the highest point of the sun in the sky defines the middle of the day for every village and harbor. Each settlement lives by its own solar time, marked by shadows that shrink and grow on stone, by bells or calls timed to the bright arc overhead. Travelers moving east or west notice that the moment of shortest shadow drifts by minutes from place to place, yet the difference is small enough to accept as part of the natural irregularity of days. It is only when distances shrink under the wheels of railways and the pulses of telegraph lines that this loose patchwork of local times begins to fracture. Trains cannot safely rely on noon that arrives earlier in one town and later in another, and messages sent along wires insist on a shared timeline able to stretch across a continent. As schedules tighten, the sky refuses to cooperate. The true sun still reaches its peak at slightly different moments at different longitudes, and the drifting equation of time still pulls apparent noon away from any single fixed hour. To resolve this tension, maps are redrawn with invisible bands that slice the planet into time zones, each zone granted a standard hour that ignores the exact height of the sun above any one location. The prime meridian is chosen to run through an observatory in a small district of London, and from that line longitudes extend east and west, each band roughly 15 degrees wide. Within a band, clocks agree with one another, even as they slip away from the local solar peak by some minutes or even by more than 1 hour near the edges. Large countries eventually compress their many natural time zones into fewer civil ones for simplicity, so that a single hour on clocks rules over regions where the sun stands at quite different angles. In some places, true solar noon comes close to the written 12. In others, it slides toward the early afternoon or approaches the late morning, leaving a quiet offset between human time and celestial geometry. Modern urban life grows around these agreed hours. Workdays, school days, and broadcasts are arranged along the grid of zone time, while the underlying dance of sun and planet continues with no regard for borders or decisions. Satellites and observatories reveal the depth of this separation. Networks of atomic clocks scattered through laboratories on several continents tick in chorus, linked by radio fiber and light. Their combined rhythm forms an international atomic time, a nearly unchanging reference that does not know sunrise or sunset. From this ensemble, a civil standard is shaped, a coordinated universal time that nations adopt as the backbone of their own zones. This standard behaves with the regularity of atoms, but Earth still spins with the slight unevenness of rock, water, and air in motion. Because of this, the alignment between atomic time and the angle of Earth relative to the sun slowly drifts. To keep them from sliding ever farther apart, small interventions are made. On rare occasions, when measurements of the planet's rotation show that its spin has lagged by a fraction of a second, timekeepers insert an extra second at the end of a chosen day. For one brief moment, the last minute of that day contains 61 seconds instead of 60. Clocks that follow atomic time pause together, allowing the world's rotation to catch up by the tiniest amount. For most people, this passing anomaly goes unnoticed, yet in that silent extra second, the link between skies and seconds is repaired. Navigation systems, observatories, and communication networks all adjust in step, for they rely both on the steady beat of atoms and on the actual orientation of Earth as it turns beneath satellites and stars. The existence of this extra second hints at something profound. Human time, even when defined by the most stable physical processes yet known, cannot fully detach from the moving world. There is no perfect abstract clock that can run without reference to the planet that inspired the very idea of a day. At the same time, the choice to add seconds or not is a decision made by committees and agencies, an act of governance layered atop physics. As some groups now propose to abandon these corrections in the future and let atomic time drift from solar time, a quiet fork appears in the history of timekeeping. One path keeps civil time close to the shifting sky at the cost of occasional small disruptions. The other path favors relentless uniformity, allowing noon on the clock to slide away from the sun's highest point over centuries. For a sleeper under the turning planet, these choices seem distant, almost invisible. Yet they shape the pattern of alarms, broadcasts, and signals that define the waking world. Beneath every appointment and schedule lies a hidden negotiation between rockstar atom and institution, each pulling on the meaning of the word day. The sun continues its apparent climb and fall, untroubled by zones and standards, while somewhere high above the surface, meteors flash briefly as they enter the atmosphere, their paths timed in fractions of a second against clocks that are themselves balanced between the steadiness of matter and the uneven spin of Earth. In that balance, local noon becomes not a single universal moment, but a shifting compromise different for every longitude, slightly restless for every date, and always traced against a background of deeper motions that never quite repeat. Beyond the familiar loop that carries Earth around the sun lies a broader motion that rarely enters ordinary thought, a path that places the entire solar system inside a larger river of stars and invisible matter. The sun does not rest at the center of the Milky Way. It orbits a dense concentration of mass near the constellation Sagittarius, where a supermassive black hole and a crowded swarm of stars shape the deep gravitational well of the galaxy. Measurements from the European Space Agency's Gaia mission show that the Sun and its planets travel around this galactic center at roughly 220 kilometers per second, completing one full circuit in about 230 million years. During a single human lifetime, the solar system traces only a small fraction of this immense loop, yet even that small fraction covers distances so vast that ordinary language struggles to contain them. While a single day passes on Earth, the star that warms it, and every planet and moon around it, advance millions of kilometers along a spiral path through the galactic disk. Nearby stars share similar motions, each following its own orbit shaped by the mass of the galaxy. To an observer riding along with the sun, many of these neighbors appear almost fixed, their slow drifts across the sky, measured in fractions of arc-seconds per year. Gaia's catalog reveals that these tiny displacements add up over centuries into sweeping migrations, clusters, dispersing streams of stars stretching and twisting, and the sun itself weaving among them. The galactic plane is not a rigid sheet. The solar system oscillates gently above and below it, rising tens of light years out of the midplane and then sinking back again over tens of millions of years. Some researchers have explored whether these vertical motions through denser and thinner regions of interstellar material might leave imprints in the history of comet impacts and climate on Earth, although the links remain under study. Even this galactic motion is only one layer of a deeper pattern. The Milky Way belongs to a small collection of galaxies called the Local Group, which includes the Andromeda Galaxy and dozens of smaller companions. Observations of Doppler shifts in the light of these systems show that some, like Andromeda, move toward the Milky Way drawn by their mutual gravity, while others drift outward along different trajectories. Over billions of years, the Milky Way and Andromeda are expected to merge into a single larger galaxy, their stars swirling together in a slow, complex collision where individual suns rarely strike one another, yet entire star fields are rearranged. Beyond, the local group clusters and superclusters link together into an enormous web of matter on cosmological scales. Studies using data from missions such as Planck and ground-based redshift surveys indicate that the local group is moving toward a broad concentration of mass called the Great Attractor, and farther structures associated with the Laniakea and Shapley superclusters. The speed of this motion, when measured relative to the almost uniform glow of the cosmic microwave background radiation, reaches hundreds of kilometers per second. This ancient light, a remnant from the early universe, arrives slightly warmer from one direction and slightly cooler from the opposite, forming a dipole pattern that reveals the motion of the entire local group through space. Thus, the coordinates of Earth are never fixed. At any moment, the planet stands at the intersection of rotational motion around its axis, orbital motion around the Sun, galactic motion around the Milky Way, and larger scale flows through the cosmic web. The resting body on a quiet bed participates in all of these paths at once without feeling even the faintest pull of acceleration, because almost all of these motions are smooth and shared by everything in the immediate environment. Inside this layered journey space, agencies build instruments that can sense and quantify movement that the human nervous system cannot. Very long baseline radio arrays spread across continents combine signals from distant quasars, which act as nearly motionless beacons at cosmological distances. By comparing how the apparent positions of these beacons shift, scientists determine how Earth's axis wobbles, how its crust deforms, and how its rotation relates to a reference frame tied to the distant universe rather than to any local horizon. Gaia plots the positions and velocities of more than 1 billion stars, creating a dynamic map of the Milky Way, where the sun's path becomes one thread among many, and where groups of stars reveal past collisions and mergers that shaped the galaxy. Satellites that measure the fluctuations in the cosmic microwave background refine the estimate of the local group's motion as it travels through the larger structure of space-time. The picture that emerges is of a universe where nothing is truly at rest. Every point is in motion with respect to something else, and every attempt to define a stationary frame turns out to be only a convenient choice. From within this perspective, the idea of standing still on the surface of Earth becomes a local illusion created by the coherence of shared travel. The bed, the building, the surrounding landscape, the atmosphere, and the nearby planets all take part in a continuous drift across the galaxy. Over the span of a single night's sleep, the solar system advances a vast distance along its orbit, and the local group slides a little farther along its path through the cosmic web. No mark is left on the skin by this crossing, yet mathematically the position in space where that sleep begins is not the same as the position where it ends. In this sense, every life is a trajectory not only through time, but through the changing geometry of the universe. The path of Earth is not a closed and unchanging circle, but a spiral folded into a larger spiral, its successive turns never passing through the same region of interstellar space twice. This realization adds another layer to the earlier questions about time. A day, a year, a century all become not only measures of rotation and revolution, but measures of how far the planet and its star have traveled through the Milky Way and beyond. Each counted interval corresponds to a specific arc traced through gravitational fields shaped by visible matter and by the unseen dark matter that holds galaxies together. Somewhere within that arc, a resting mind drifts into sleep, unaware that its dreams unfold on a moving world carried along by structures that stretch from the scale of oceans and mountains to the scale of clusters and superclusters. The familiar sense of location shrinks to the size of a room, while the true position of that room becomes a point sliding through a universe that does not pause. For most of human history, a day appears simple, a span of light and darkness counted as 24 hours between one midnight and the next. Yet beneath this familiar measure, another quieter clock turns with a different rhythm. The solid body of Earth completes one full rotation relative to the distant stars in a little less than 24 hours. About 23 hours, 56 minutes, and 4 seconds, a period known as the sidereal day. During that time, the planet also advances along its orbit around the Sun by nearly 1 degree, so that when one full spin with respect to the stars is finished, the Sun is not yet back to the same place in the sky. To bring the star of the day once more to the same position over a given longitude, Earth must rotate a small extra angle, taking roughly 4 additional minutes. The result is that the solar day, the interval from one noon to the next, becomes slightly longer than the sidereal day, and the 24-hour cycle that shapes clocks and calendars is built on this combined motion rather than on pure rotation alone. This extra twist is small, but its effects accumulate steadily. Because the stars mark the sidereal rhythm instead of the solar one, they rise about 4 minutes earlier each night by human clocks. Over the span of 1 month, this shift amounts to roughly 2 hours, and over half a year it amounts to almost half a day, causing constellations that dominate one season's sky to slip below the horizon in another. This slow migration of familiar patterns becomes an unhurried celestial calendar. Observers in ancient deserts, forests, and islands learn that certain star groupings climb at dusk when particular winds arrive, or when seasonal rains approach, and the sidereal sky becomes a guide to planting, sailing, and ceremony. In modern times, the same difference between sidereal and solar time becomes an engineering requirement. Large observatories mount their telescopes on axes aligned with Earth's rotation so that electric motors can turn them at the sidereal rate, matching the apparent motion of the stars. When the drive engages, a galaxy billions of light years away can remain centered on the detector despite the planet's spin, its light gathered patiently over long exposures while Earth rotates beneath the instrument. Space telescopes in orbit use similar principles, locking onto guide stars whose positions have been charted with exquisite care by missions such as Gaia. In all of these systems, sidereal time serves as an invisible coordinate grid draped over the turning world, allowing distant objects to be followed with precision, while the everyday 24-hour cycle fades into the background. Yet the sidereal day itself is not perfectly constant. The length of Earth's rotation changes by tiny amounts under the influence of ocean's atmosphere and the gravitational pull of the moon. Tidal bulges raised in the seas drag very slightly against the seafloor as the planet turns, converting rotational energy into heat and causing the spin to slow over millions of years. The moon in turn drifts gradually farther away as it gains energy from this exchange. Ancient corals and layered tidal sediments preserve a record of this process, revealing that hundreds of millions of years ago, Earth completed more days during a single orbit around the Sun, meaning each day was shorter than it is now. Today, the change is far too small for the unaided senses, but instruments can detect it. Radio arrays that compare signals from distant quasars measure how Earth's orientation shifts relative to the distant universe. Laser pulses bounced from reflectors left on the Moon and from satellites in high orbit refine the knowledge of the planet's exact rotational state. Together, these techniques allow agencies such as the National Aeronautics and Space Administration and other institutions to track the length of day to a precision of microseconds, uncovering irregularities caused by changes in wind patterns, ocean currents, and the slow rebound of crust once weighted down by ancient ice sheets. When these measurements are compared with atomic time, a small mismatch grows, and caretakers of global timekeeping must decide when to insert a leap second so that the tally of seconds remains close to the actual rotation of the Earth. Thus, the difference between the sidereal day and the solar day and the slow evolution of both turns into a meeting point between distant galaxies used as reference marks and the ceaseless movement of water and air around the planet. The sleeper on the night side lives entirely by the solar day rising and resting according to the pattern of sunlight, yet overhead, the sidereal day continues to mark a separate, slightly faster beat. Each clear night, if one could remain awake and attentive, would show the same star crossing the same point in the sky a few minutes earlier than the night before, as if an unseen hand were turning a vast dim wheel. Other planets around distant stars would carry their own hidden offsets between starlight and daylight, their own slow drifting constellations, and changing counts of days per orbit. In this context, the terrestrial day of roughly 24 hours split into solar and sidereal versions that almost but not quite match becomes one more local compromise in a universe where time is always tied to motion and where every spinning sphere writes its own definition of how long it takes for morning to return. The Earth does not only spin and orbit, it leans. Its axis tilts by about 23.4 degrees relative to the plane of its path around the Sun, and this small lean quietly governs seasons, storms, and migrating bands of climate that circle the globe. From a distance, the planet appears as a spinning sphere that never quite stands upright, its poles tracing gentle circles in space, while the tilted axis holds nearly the same direction as Earth moves along its orbit. Because of this geometry, each hemisphere takes turns bowing toward the Sun and then turning away. When the northern hemisphere tilts sunward, sunlight arrives at a steeper angle and lingers longer across land and sea, concentrating energy into shorter nights and warmer days. The southern hemisphere at the same time receives light spread over a wider area and for fewer hours, cooling into winter. Half an orbit later, the situation reverses. The change in season follows from the quiet constancy of a lean that never straightens. At the equator, the sun climbs high in the sky almost all year, and the lengths of day and night remain close to equal, while toward the poles the tilt brings long periods of light and darkness. Inside the Arctic Circle, there are weeks when the sun never sets, and other weeks when it never rises, leaving the landscape in a long twilight that can last for months. This behavior once puzzled observers, who assumed that distance from the sun must decide temperature. In fact, the Earth is slightly closer to the sun during northern winter than during northern summer, yet snow and ice dominate one season and retreat in the other. Agencies such as the National Aeronautics and Space Administration describe how the angle of sunlight, not the small change in distance, sets the strength of seasons. The tilt determines how much solar energy falls on each square meter of ground and how long that ground remains illuminated. Observations from orbit show the belt of maximum heating sliding north and south over the course of a year as the point of overhead sun moves between the Tropic of Cancer and the Tropic of Capricorn. The axial lean also shapes global circulation. Bands of rising warm air near the equator, sinking dry air in the subtropics, and storm tracks in mid-latitudes all respond to how sunlight is poured onto the rotating sphere. As one hemisphere leans more directly into the sun, jet streams shift and monsoon systems strengthen or weaken. Yet the tilt is not perfectly constant. Over tens of thousands of years, gravitational tugs from the moon and the other planets cause the angle of Earth's axis to vary between about 22.1 degrees and 24.5 degrees. This slow breathing of the tilt is one part of a family of changes known as Milankovitch cycles, which also include slight shifts in the shape of Earth's orbit and the direction in which the axis points in space. Geological records taken from deep ice cores and ocean sediments show that these cycles line up with the advance and retreat of ice sheets and with long swings between colder and warmer climates. When the tilt grows larger, summers become hotter and winters colder, especially at high latitudes. Stronger summers can melt more ice, reducing the planet's reflectivity and allowing more solar energy to be absorbed. When the tilt shrinks, seasons soften and polar regions receive less summer light, allowing ice to survive and spread. In this way, a variation of only a few degrees can help steer the planet between glacial and interglacial states over many tens of thousands of years. The presence of the moon appears to steady this behavior. Computer models that remove the moon from the system often find that Earth's tilt would wander by much larger amounts, swinging under the influence of other planets and perhaps making climate far less stable. With the moon in place, the axial angle still changes, but within a narrower band, giving long-term climate a degree of regularity that may have been important for the evolution of complex life. Spacecraft and ground observatories measure the orientation of Earth's axis by tracking stars and quasars, tying the direction of the poles to reference points far beyond the solar system. Over time, their data show the slow precession of the axis like a spinning top whose handle sweeps out a circle in the sky, completing one loop in roughly 26,000 years. This precession gradually shifts which star lies near the north celestial pole and alters the timing of seasons relative to Earth's position in its orbit. Thousands of years ago, a different star marked north, and thousands of years from now, another will take its place, even though to anyone standing beneath the sky on a given night, the change from year to year is imperceptible. Within a single human lifetime, the tilt feels fixed. The pattern of spring, summer, autumn, and winter repeats with dependable familiarity, and seasonal rituals form around that repetition. Yet within stone, ice, and orbit, instruments detect a more intricate story in which the planetary lean slowly shifts the axis, slowly turns, and the delivery of sunlight is subtly reshaped over cycles longer than recorded history. From this perspective, each season becomes a brief note in a much longer piece of music, and the familiar march of weather and daylight is part of a composition written by gravity acting on a tilted, rotating sphere, while a resting body experiences only a few moments of that wider, almost silent song. Among the many rhythms layered into Earth's motion, one of the quietest is the small mismatch between the length of a day and the length of a year. The planet completes one orbit around the sun in a span known as the tropical year, measured from one vernal equinox to the next. That span is a little longer than 365 days and a little shorter than 366 days, about 365.242 days. Calendars, however, are built from whole days. A year of 365 days runs slightly short. A year of 366 days runs slightly long, and the tiny remainder refuses to vanish. Left alone, that remainder would slowly pull the written date away from the seasons. The midpoint of winter on the page would creep toward spring, the height of summer would drift toward autumn, and after enough generations the familiar association between month and season would unravel. Early skywatchers noticed this drift by comparing the behavior of rivers' crops and constellations to the days kept in their societies. At first the remedies are rough adding days, or even months when the mismatch grows obvious. Later in the system that becomes known as the Julian calendar, a clearer rule takes shape. The year is treated as 365 and 1/4 days long, and to account for the extra quarter, one additional day is added every fourth year. This produces an average year of 365.25 days, close to the true value but not exact. The remaining difference, only a handful of minutes each year, stacks quietly through the centuries. Equinoxes and solstices arrive earlier and earlier in the calendar. The vernal equinox in the northern hemisphere, once near the 21st day of March, drifts toward the middle of the month. Festivals tied to that turning point slide with it, and the gap between printed date and sky becomes impossible to ignore. A second refinement follows. Under what becomes the Gregorian calendar, several dates are removed from a chosen year so that the equinox returns to its older place. At the same time, the leap year rule is sharpened. Years divisible by 4 remain leap years except for century years, which lose their leap day unless they are also divisible by 400. This pattern drops 3 leap days out of every 4 centuries, trimming away the small excess left by the earlier system. The result is an average calendar year that almost exactly matches the tropical year, with only a faint residual difference that would take thousands of years to build into a whole day. In some countries, the change happens early, in others much later, so that for a while 2 parallel calendars coexist. From far above the plane of the solar system, this entire episode would appear as a minor adjustment in human counting, a slight reshaping of numbers so that dates better track the unchanged path of a tilted planet around its star. From the ground, it introduces a curious feature into experience, a rare day at the end of February that appears only in certain years, an extra step in the staircase of time that quietly encodes the fraction hidden in Earth's orbit. Modern observatories and space agencies use this refined calendar as one layer in a more intricate system. When plotting the positions of planets or planning the path of spacecraft, they often translate calendar dates into continuous counts of days and fractions of days since an agreed starting point. These smooth counts ignore the uneven lengths of months and the sudden appearance of leap days, allowing the equations of motion to unfold without interruption. Behind the familiar grid of months and years, a quieter numerical line connects real motion to prediction. In this layered picture, leap years and leap days are not errors but gentle corrections. Small regular pulses that keep civil time tethered to the cycles that first gave meaning to the word year. On shorter scales, a similar story unfolds. Atomic clocks define the second using the steady rhythm of atoms, more uniform than the spinning Earth can provide. Compared to this standard, the length of a day wanders by tiny amounts as winds shift, oceans move, and the moon's pull slowly alters the rotation. To keep the count of atomic seconds close to the turning of the planet, international timekeepers sometimes add a leap second, an extra counted heartbeat of time inserted at the end of a chosen minute. A leap day answers the fractional part of a day left over in each orbit. A leap second answers the subtle irregularities in the spin of the globe beneath the sky. Both exist because the universe does not arrange its cycles in simple whole numbers. Instead, human systems bend around the facts of motion, trimming and adding moments so that the abstract grid of dates and hours continues to cling to the moving world. Far ahead, as gravitational pulls slowly reshape the orbit and the length of the tropical year itself evolves, new refinements may be needed. For now, each rare 29th day of February and each almost unnoticed extra second marks a moment when the arithmetic of the calendar touches the geometry of Earth's path, somewhere on the dark side of the planet. While such adjustments are calculated and agreed upon, a resting body sleeps through an ordinary night, unaware that time itself is being gently nudged to keep pace with a world that never turns or travels in perfectly simple ratios. The journey of a single human lifetime unfolds not only through memories and events, but through an immense physical path that winds invisibly through space. From the moment a newborn first inhales air, the body that holds that breath rides on a rotating planet that circles a star, which itself circles the center of a galaxy, drifting through the larger structure of the universe. Over what is considered a long life, perhaps 100 years, this layered motion carries every cell, every heartbeat, and every hour of sleep across distances that dwarf any map drawn on paper. Even a single day is a voyage of surprising scale. As Earth rotates, a point near the equator travels roughly 40,000 kilometers in one full turn. During the same span, the planet moves about 2.5 million kilometers along its orbit around the Sun. Meanwhile, the Sun and its planets advance many millions of kilometers around the center of the Milky Way, and the entire local group of galaxies slides through the cosmic web at hundreds of kilometers per second. Multiply these distances by the number of days in a lifetime, and the path traced by one human being who may feel confined to a city or a small region reaches into the billions of kilometers. The traveler does not notice because almost all of this motion is shared. The bed, the house, the surrounding landscape, and the air all move together. Within this shared frame, motion that is smooth and unchanging becomes invisible. Only changes in speed or direction produce forces that muscles and inner ears can sense. There is no special state of absolute rest, only different frames of reference, each carrying its own version of stillness. A person resting in a quiet room on Earth is at rest in the terrestrial frame, yet in rapid motion in a frame tied to the center of the Sun, and in a more rapid motion still in a frame tied to the center of the galaxy. Instruments built by space agencies reveal the scale of this journey in ways that the body cannot. Spacecraft that leave Earth carry clocks and sensors which record how their trajectories unfold through the solar system. Observations from the Gaia spacecraft map the motion of the Sun relative to nearby stars and the larger Milky Way, showing that every human life is embedded in this slow galactic orbit. In principle, one could mark the position where a person was born in a coordinate system tied to distant quasars, and then mark the position where that same life ends. The difference between these 2 points would form a long sweeping segment of a spiral path through the galaxy, tens of billions of kilometers in length. Small voluntary motions, walking, running, flying in aircraft, add only short loops and deviations to this far larger curve. The idea that every life is a voyage along such a path raises subtle questions about what is meant by location. Ordinary language tends to tie place to the surface of Earth, to cities, landscapes, and coordinates measured in latitude and longitude. Yet those coordinates ride on a crust that is itself drifting on slowly moving tectonic plates which rest on a convecting mantle inside a planet spiraling around a star. The true position of any point must therefore be given not only relative to Earth but relative to the solar system, the galaxy, and the larger flow of matter in which that galaxy is embedded. For most purposes, such precision is unnecessary. Navigation architecture and daily life all function well using a frame attached to the rotating planet. Still, the awareness that this frame is temporary, sliding through space, introduces a quiet sense of impermanence. The place where a childhood memory forms is not the same place in space where that memory is recalled decades later, even if the person stands on the same patch of ground. The ground has moved on. Technology that relies on precise timing carries traces of this deeper journey. The Global Positioning System, a constellation of satellites orbiting Earth, uses atomic clocks whose readings must be corrected for both motion and gravity. Without these adjustments, the system would accumulate errors of many kilometers each day. Indirectly, every time such a system is used to find a route or to measure a distance, the calculation includes a recognition that Earth is a moving platform and that time on that platform is shaped by motion and gravitational field. Astronauts who spend long periods in orbit experience time at a slightly different rate from those who remain on the ground, and when they return, careful comparisons of clocks reveal differences measured in fractions of a second. Everyday life contains the same principles in gentler form. Every step, every journey by car or plane, every night of sleep on a rotating planet inside a moving solar system contributes to a personal path through space-time, a continuous curve that links birth to death. Physics treats this curve as one object among countless others, each describing how matter and energy move through the universe. For the consciousness carried along it, that curve is lived as a sequence of moments that feel local and still. The contrast between these two views, between the cosmic path and the ordinary room, suggests that neither description of a life is complete on its own. One story speaks in small distances and familiar places, another in orbits and galactic motion. Together they point toward a larger picture in which a fragile living system persists for a while on a planet that never stops moving through a universe that never rests. In the long history of timekeeping, one of the strangest episodes unfolds, not in the motions of planets or stars, but in the pages of human calendars, when entire days vanish by decree, while the Earth itself continues to turn without interruption. For centuries, the Julian calendar, with its simple rule of adding one extra day every fourth year, guides civil and religious life across large parts of the world. It treats the year as 365 and 1/4 days long, a value close to the tropical year, yet slightly too generous. The true interval between vernal equinoxes shaped by the tilt of Earth's axis and the slow precession of that tilt through space is a little shorter than this neat fraction. Each year the calendar runs ahead by a matter of minutes. Each century the drift grows into days. Festivals tied to the sky move away from their intended seasons, and the dates that once marked the arrival of spring begin to fall against a winter sky. By the 16th century, the mismatch between the Julian dates and the actual position of Earth in its orbit is large enough to trouble astronomers and religious authorities alike. The vernal equinox, which earlier generations associated with a particular date, now arrives roughly 10 days earlier in the calendar. The sky has not changed its pattern, but the human system that labels days has slipped. To repair this, scholars propose a correction that sounds simple but carries a peculiar consequence for daily life. A new rule for leap years will bring the average length of the calendar year closer to the length of the tropical year, and at the same time, a block of dates will be removed, once as if time between certain midnights did not exist at all. Under what becomes known as the Gregorian reform, 3 leap days are dropped out of every 4 centuries by changing the way century years are treated, and in the first year of adoption, several dates in early October are skipped, so that the calendar jumps forward and the equinox once again aligns with a more traditional page. People go to bed on one date and wake to find that the next morning is numbered 10 days later. From the viewpoint of celestial mechanics, nothing unusual occurs. Earth spins smoothly through the same sequence of rotations. The moon continues its orbit, and the sun shines on landscapes that do not miss a single dawn. Yet within human records, 11 days or 10 in some regions at first are absent. Contracts, diaries, and legal documents bridge a gap in counting that the cosmos does not recognize. In some places, the sudden disappearance of days causes confusion and unease. Stories circulate of protest demanding the return of stolen time, whether or not these events happened in the vivid way later accounts describe. What is certain is that individuals living through the change must adjust birthdays, feast days, and anniversaries, and that some who are paid by the day worry that they have lost part of their income to an invisible correction. In reality, wages and obligations are often arranged to flow smoothly across the reform, but the sense that time itself can be edited leaves a mark. From a modern perspective, supported by observations from space agencies and precise measurements of Earth's rotation, the reform appears as a careful synchronization of a human timekeeping system with the orbital behavior of a tilted planet. The days that vanish from the calendar do not vanish from the history of motion. Rather, they represent a realignment, a decision to shift the labels on the stream of days so that they better match the turning of the globe and the timing of equinoxes and solstices. The episode reveals how malleable civil time can be and how rigid celestial time remains. Atomic clocks and space-based instruments now allow the length of a day and the timing of seasons to be measured with far greater precision than the scholars of the 16th and 18th centuries could imagine. When these modern systems show that the rotation of Earth drifts slightly with respect to the uniform ticks of atomic time, the response is once again to adjust the human count. Leap seconds are introduced in rare years, adding a single extra second to the final minute of a chosen day. The scale of the change is tiny compared to the 11 days that once disappeared, yet the principle is similar. Human time is periodically edited to remain in harmony with a moving planet. The possibility arises that in the distant future, new reforms will be needed as gravitational interactions slowly alter the length of the day and the year. From the standpoint of an observer looking down on the solar system, these corrections are small ripples in the way intelligent life chooses to number the cycles of a world. From within human society, they are moments when the flow of time feels briefly negotiable, when the realization surfaces that dates and hours are agreements laid over motions that do not consult those who name them. The 11 missing days become an enduring symbol of this tension. They demonstrate that time as lived and time as measured by orbits are not the same, and that bridging the gap involves occasional deliberate acts of erasure and insertion that leave untouched the deeper, continuous turning of Earth beneath the stars. Atomic timekeeping emerges from the desire to step beyond the irregularities of spinning planets and drifting calendars to define a second that does not depend on the behavior of Earth or the apparent motion of the Sun. In laboratories cooled and shielded from noise atoms of a chosen element, are guided and measured so that the frequency of a particular transition between energy levels can be used as a reference. The official definition of the second is tied to such a transition in the element cesium, whose internal rhythm proves remarkably stable when isolated from disturbances. In this definition, a second is no longer 1/86th of a rotation or a fraction of a day. It is a certain number of oscillations within an atom a unit drawn from the microscopic fabric of matter. Arrays of atomic clocks built by metrology institutes on several continents compare their readings, and their averaged output forms an international atomic time scale, a nearly unbroken sequence of seconds that ticks forward without regard for sunrise season or orbit. This development seems at first to separate human time entirely from celestial motion, yet the deeper it is examined, the more connections reappear. Relativity insists that even atomic clocks do not agree unless their motion and gravitational environment are carefully accounted for. A clock on a mountain runs imperceptibly faster than one at sea level because gravity is slightly weaker at higher altitude. A clock carried on an aircraft or an orbiting satellite traces a different path through space-time than one fixed on the ground, and its seconds lengthen or shorten accordingly when compared. Engineers building global navigation systems must calculate these differences in advance and program corrections into the satellites. Otherwise, the positions those systems return would wander by many meters each moment and far greater distances as days pass. The uniformity of atomic time thus proves to be local rather than absolute. The attempt to build a perfect clock reveals instead a field of slightly different clocks, each linked to its surroundings by the geometry of space-time. New generations of timekeepers push this sensitivity further. Optical lattice clocks, which use atoms trapped in patterns of laser light and transitions at much higher frequencies than cesium, achieve such precision that they can sense gravitational differences across a height of only a few centimeters. Placed in different rooms of the same building, they reveal a subtle hierarchy of time, with higher floors aging fractionally faster than lower ones. In principle, a dense network of such clocks spread across a continent could map the strength of gravity in detail, tracing underground structures, fluctuating water tables, and perhaps even tiny tremors before they are felt as quakes. Time itself becomes a probe of the planet, a measurement not merely of duration but of depth and mass. Far beyond Earth, astronomers apply similar thinking to the universe as a whole. The glow of the cosmic microwave background, the afterlight of an early hot phase, provides a kind of cosmic timestamp. Its properties allow cosmologists to estimate how long it has been since the universe expanded from a denser, hotter state. Yet even this cosmic age is defined within a particular frame, one in which the microwave background appears nearly the same in every direction. A galaxy racing at high speed relative to this frame would slice the history of the universe into different layers of simultaneity. There is no single master clock that all galaxies follow. Instead, each world line carries its own proper time, and any shared chronology must be carefully defined. Space observatories that look back toward the earliest galaxies act as both telescopes and time machines. The finite speed of light ensures that distant objects are seen not as they are now, but as they were when their light began its journey. The deeper a telescope looks, the further into the past it peers. Images of galaxies billions of light years away show them in their youth undergoing rapid star formation, colliding and merging in ways that shape the structures visible in the present. An observer exploring such data moves not only through coordinates on the sky, but through layers of time, comparing young galaxies to older ones, and building a narrative of cosmic evolution that depends on a chosen cosmological clock. In this framework, atomic seconds, planetary days, and galactic ages all appear as different expressions of a more general concept: time as the ordering of change. Instruments convert oscillations into seconds, orbits into years, and the redshift of distant light into billions of years since emission. Yet none of these measures exists independently of the processes that define them. If all change were to cease, if no particle moved and no field varied, the equations suggest that time would lose meaning. The steady ticking of even the most refined clock requires motion at some level. This leads some thinkers to wonder whether time is a fundamental component of reality, or an emergent property that arises from the way many interacting parts rearrange themselves. Experiments aimed at unifying quantum theory and gravity probe regimes where the familiar flow of time may break down or take on unfamiliar forms. For now, the clocks on Earth continue their work comparing rotations, orbits, and atomic transitions with growing nuance while a quiet human life unfolds among them, marked by moments that feel either fleeting or long, even though each occupies roughly the same number of measured seconds. Between these perceptions and the instruments that tally durations, a gap remains hinting that the full nature of time may be more elusive than any definition drawn from atom stars or galaxies alone. Within the body that rides these orbits and rotations, another kind of clock keeps time, one that does not count seconds or track stars, but responds instead to cycles of light and darkness, filtering through the atmosphere of a turning world. Deep in the brain, groups of cells form what biologists call circadian rhythms, patterns of activity that rise and fall over roughly one day. These rhythms help govern the release of hormones, the timing of sleep and waking, and the ebb and flow of alertness and body temperature. Long before mechanical clocks, these internal cycles align to the external pattern of sunrise and sunset itself, set by the rotation of Earth. Even now, inside cities bright with artificial light, the ancient link between spinning planet and living tissue remains. Light entering the eye at morning quiets the production of melatonin, a hormone that encourages sleep and signals the body that a new day has begun. Darkness at night allows melatonin to rise again, inviting rest. Astronauts aboard spacecraft in low orbit experience many sunrises and sunsets each terrestrial day as they circle Earth in about 90 minutes. Yet their bodies still seek a single stable 24-hour rhythm, guided by scheduled periods of light and dark, arranged by mission planners, drawing on research from agencies such as NASA. In this way, physiology chooses its own frame of time, one that uses the rotation of Earth as a template, even when the immediate environment offers a different cycle. When a person travels rapidly across time zones, the local civil time jumps compared to the internal clock. The sun may rise at what the body perceives as the wrong hour, mealtime shift, and sleep becomes disturbed. Over several days, signals from light and behavior gently pull the internal rhythms toward the new schedule, realigning biology with the clock on the wall and the pattern of daylight at that longitude. The discomfort known as jet lag is a reminder that time has more than one meaning. There is clock time defined by seconds and minutes, and there is body time defined by cycles of chemistry that cannot be reset instantly. Both are grounded in the same underlying rotation of Earth, but they respond to it with different degrees of delay and inertia. Even perception itself does not track time in a uniform way. Moments filled with rich or threatening events may feel stretched, while long periods of repetition seem to pass quickly when recalled. The physical duration is the same in both cases, but memory and attention weight them differently. Quiet, predictable intervals lay down sparse traces, while surprising or intense intervals leave denser patterns. From the viewpoint of physics, both intervals span the same number of seconds, but from the viewpoint of lived experience, they are not equivalent. This divergence adds another layer to the picture built from orbits, rotations, and atomic oscillations. There is cosmological time measured from the glow of the early universe, planetary time measured in days and years, atomic time measured in cycles of radiation, and biological time measured in pulses of hormones and waves of neural activity. None of these is entirely independent of the others, yet none reduces completely to another. A resting person in a darkened room near midnight participates in all of them at once. The internal clock drifts toward its nightly phase, melatonin rises, heart rate slows, and the brain prepares to enter patterns of activity that differ from waking consciousness. Outside, the local time zone defines midnight by convention, while the sun stands below the horizon because the planet has rotated that region away from direct light. Farther out, the solar system has advanced another step along its orbital path through the galaxy. Instruments may note these changes, but the mind letting go into sleep experiences only a gradual fading of thought and a reshaping of awareness. Space agencies monitoring crews on long missions pay close attention to these biological rhythms because performance and health depend on keeping internal cycles in reasonable alignment with work and rest schedules. In this sense, every heartbeat and breath is already a response to cosmic motion. The familiar idea of a natural day experienced as a pattern of waking, eating, working, and sleeping is an emergent result of a tilted sphere rotating under a distant star. If Earth rotated significantly faster or slower, or if its tilt and orbit produced a different pattern of light and dark bodies and minds, would have evolved different internal clocks. The 24-hour rhythm often feels like an intrinsic feature of life itself, yet it is more accurately a negotiated truce between the needs of living chemistry and the specific rotational period of this world. Sleep does not simply arrive at the end of some arbitrary number of hours. It emerges at the intersection of internal cycles and external cues themselves rooted in the turning of a planet whose motion is part of a chain reaching from bedroom to horizon to star field to galaxy. Somewhere beyond the walls, the night sky shines as a delayed record of ancient events while inside neurons slow their chatter and the boundary of awareness narrows. Between these scales, between cosmic time and body time, the idea of a single simple flow of moments becomes harder to sustain. Instead, time appears as layered motion and layered change, from the paths of galaxies to the flicker of nerve cells, all overlapping, to produce the quiet sense of evening that settles over one small moving world. Long before atomic clocks and orbiting satellites, the link between time and place begins to reveal itself on the surface of the oceans. Sailors can find latitude by the height of familiar stars above the horizon, but longitude, the east-west position of a ship, remains elusive for centuries. A vessel can drift slowly off course without anyone realizing until land appears where none was expected or fails to appear where charts insist it should. The problem is not only one of distance but one of time. To know how far east or west a ship has traveled, navigators must compare the local solar time on board, marked by the height of the sun above the sea, with the time at a fixed reference point elsewhere on Earth. Each hour of difference corresponds to about 15 degrees of longitude. Without a reliable clock that can keep the reference time across weeks of rough motion and changing temperature, the calculation dissolves into guesswork. Attempts to solve this rely first on celestial tables and on measurements of the moon's position against background stars, a method that demands clear skies, complex charts, and long calculations. Eventually, craftsmen build mechanical timekeepers robust enough to survive life at sea and accurate enough to keep land-based time for long voyages. Once these marine chronometers exist, longitude becomes a matter of comparing noon on deck with noon at the reference meridian, allowing position to be fixed more securely on a turning globe. A ship moves across the curved surface, while its clock carries the rhythm of a distant port. Each comparison between shadow and clock face collapses the gap between the local sun and the standard time, revealing the vessel's place in both dimensions. In this way, the surface of Earth is mapped by differences in time. Every longitude band is defined by how many hours earlier or later local noon arrives compared to a chosen line. The planet's rotation turns into a vast dial whose different points read different hours at once. When time zones are later formalized for rail travel and communication, This same link between time and place is written into law. A coarser grid replaces the continuous drift of solar time, but the principle remains: position around the axis corresponds to offset in time. In modern navigation systems, the role of marine chronometers is taken over by constellations of satellites in high orbits. Each satellite carries atomic clocks tuned and corrected to account for motion and gravity. They broadcast signals that include both precise timestamps and information about their own positions. Receivers on the ground listen to several of these signals at once. By comparing the time each one arrives with the time it was sent, and by knowing how far light travels in that interval, the receiver can calculate its distance from each satellite. Where these spheres of distance intersect, the receiver finds its own coordinates on or near the surface of Earth. The process is a three-dimensional echo of the old longitude method, but now the reference times come from machines high above, and the calculations are performed by algorithms rather than by hand. In this picture, location is derived directly from time differences. Without the shared rhythm of atomic clocks in space and on the ground, the system collapses. Telling where becomes inseparable from telling when. Even deep space missions rely on a similar principle. Spacecraft far from Earth send back radio signals that take minutes or hours to arrive depending on distance. By recording the time of transmission and the time of reception, mission control determines how far the craft is and refines its trajectory. Networks of antennas spread across continents track these signals, allowing engineers to chart a path through the solar system that depends on accurate knowledge of both motion and delay. The farther a vehicle travels from the planet, the more its story becomes a sequence of times and positions woven together, each entry dependent on clocks that were originally calibrated on Earth. The same logic appears in astronomy itself. To locate a star precisely in the sky, observatories need to know the exact orientation of Earth at the moment of observation, which in turn depends on the time since a reference position. Instruments that measure Earth's rotation relative to distant quasars provide this connection. The sky becomes a fixed backdrop against which the turning of the world is measured, and every measurement of a star's coordinates contains hidden information about when that measurement was taken. On smaller scales, a person standing at a street corner may glance at a device that shows both time and a map. The icon marking position appears stable, yet the system that produces it is the result of signals crossing space at finite speed of orbits slowly decaying, of relativistic corrections to atomic transitions, and of decades of refinement in understanding how a rotating orbiting planet moves beneath a sky that offers no absolute frame. Behind the simple display lies a dense layering of timekeeping and motion. From this vantage, the idea of time as something separate from space begins to blur. Place on a turning Earth is partly defined by the angle of rotation, which is itself counted in time since an agreed reference. Orbits and trajectories are described by how long it takes to move from one point to another, while the definition of a second comes from internal motions in atoms. To say that a ship, a satellite, or a human is somewhere is to refer often implicitly to a whole structure of clocks and paths. Each coordinate, whether on sea, land, or in deep space, is anchored to the geometry of motion through time. This intertwining suggests that mapping the cosmos is not only a matter of drawing lines in space, but also a matter of tracing how processes unfold. A chart of the universe that attempts to ignore time would freeze galaxies and stars in positions they do not hold for long, while a chart of pure times without places would lose the context in which events occur. In practice, every astronomical map is stamped with an epoch, a date that declares which slice of the moving sky it represents. The map is true for that moment and slowly diverges thereafter as stars shift and planets move. In this sense, navigation, whether across oceans, continents, or interstellar distances, is always an act of moving through space-time rather than through space alone. A resting body under a spinning sky does not feel this complexity. Yet whenever a path is planned, a journey timed, or a position checked against a chart, the quiet dependence of place on time reveals itself again. A reminder that on a world that never stops moving, knowing where something is cannot be separated from knowing when it is measured. Bandanoy continue viewed from a great distance. Earth becomes a small luminous sphere, tracing a path around a yellow star, its thin atmosphere tinted by scattered light, and its night side dotted with faint artificial glows. From farther still, the sun and its planets shrink into a bright knot of motion within a spiral arm of the Milky Way, one node among many in a web of galaxies that stretches for billions of light years. At each of these scales, motion dominates the picture. The planet spins, the star orbits, the galaxy drifts, and the entire structure rides the expansion of space-time revealed by the redshift of distant light. Yet within this restless arrangement, pockets of calm emerge where motion is shared so completely that it becomes invisible. A quiet room on the night side of Earth is one such pocket. The bed, the air, the walls, and the resting body all travel together, following the same rotations and orbits, feeling only the constant downward pull of gravity, and none of the vast speeds that define their trajectory through the universe. Time inside that room is measured in slow breaths, in the gradual loosening of muscles, and in the fading of thoughts into dreams. Outside time is measured in the turning of constellations across the window, in the advancement of the planet along its orbit, and in the imperceptible rearrangement of the Milky Way stars as recorded by instruments. Deeper still, time is measured in oscillations of atoms within distant laboratories, in the tick of atomic clocks aboard satellites, and in the lengthening wavelengths of ancient photons that left early galaxies and now arrive as a faint cosmic background. Beneath all of these measures lies entropy's arrow guiding the universe from less probable arrangements of matter and energy toward more probable ones, quietly setting the direction from which memories are drawn and into which predictions must reach. In this layered world, the familiar idea of a day or an hour becomes only one way of slicing change into units. Days arise from rotation, years from orbit, seconds from atomic transitions, and subjective moments from patterns of neural activity. None of these is entirely fundamental, yet all are indispensable within their own domains. An astronomer tracking an exoplanet relies on precise sidereal time to keep a telescope trained on a star. An engineer guiding a spacecraft through a gravity assist uses atomic time and relativistic corrections. A navigator on a ship or a pilot in an aircraft trusts satellite signals that transform differences in arrival times into positions on a rotating globe. A sleeping mind, meanwhile, needs none of these explicit measures. It follows its own circadian cycles, responding to light, darkness, and the chemistry of the brain. All of these timelines intersect on the same moving sphere. Geological strata store records of past climates shaped by variations in tilt and orbit. Ice cores hold trapped bubbles of air that reveal how the atmosphere changed as ice ages advanced and retreated, their layers counted like pages in a book written in snow. Fossils trace the evolution of life across eras, each species adapting to a world whose days slowly lengthened and whose seasons changed rhythm under slow celestial cycles. Above telescopes record the changing brightness of stars and the subtle drift of galaxies as dark energy drives cosmic expansion. The present moment for any observer is the thin boundary where all these histories meet, carried on a planet that is itself a temporary structure in a universe still unfolding. The sense that time flows evenly from past to future while space provides a stable stage is replaced under close examination by a more intricate picture in which space-time forms a single fabric and motion through one dimension influences experience of the other. The resting body, unaware of the vast calculation, lies near the bottom of an atmosphere held close by gravity on land, shaped by cycles of erosion and uplift, under constellations whose light began its journey long before any current life existed. On the scale of galaxies, the interval between lying down and waking is a barely noticeable step in a long orbit. On the scale of personal experience, it can be a profound separation between one day's concerns and the next. In this contrast lies a quiet mystery. The same physical laws that describe the expansion of the universe and the bending of light near black holes also govern the chemistry of a single neuron and the spiraling structure of a sleeping breath. The restless motions of earth and sky create the conditions for small sheltered places where stillness and rest are possible. Whether time itself is a fundamental ingredient of reality or an emergent feature of patterns changing within a deeper structure remains uncertain. For now, the only clear fact is that every second, however it is defined, is entangled with motion. Every moment of apparent rest is supported by vast trajectories that began long before and will continue long after any one observer's life. The question of what time truly is beyond these intertwined motions and measures remains open, a quiet space at the edge of knowledge, as Earth continues its spin into another unnoticed fraction of its journey around the sun.